Okay. So today we are going to learn one very important aspect, that's called PWM, which is very important for inverter switching. So already yesterday we discussed about the pre-charging. Okay, we already discussed about pre-charging. So say the equivalent circuit already I have drawn. Say this is the capacitor, and this is the initial charge of the capacitor. Now, as I told, here to restrict the induced current, we need to add here some resistance. Say it is R. Okay, so this is 1 by CS. This is 1 by CS, and that is VC0, VC plus, VC0 plus, that one you can tell, by S. And say this is the voltage we are connecting across the capacitor for charging. So this is Vs. So now the current flowing through the circuit, that is equal to Is is equal to, I am assuming initially the capacitor is not charged, so this part is not there, so it is Vs by R plus 1 by CS. Okay, this one. And you can suppose, if you want to simplify, now from here you can find out the instantaneous current IT. Okay, so that current will be this V by R. So basically, if you go to the inverse Laplace transform, so it will be say V. This I am considering it is a constant voltage, so it will be V by R into e to the power minus T by RC. Okay, so it will come in this form. So if you know the peak rating of the power supply, then this is basically it is an exponential function. So if you plot here this one, so if you plot this, it will come like this. So this is at t is equal to 0, this will be the maximum current. So now if you know the peak rating, this current basically this is V by R. So if you know, and similarly you can find out compute the voltage also. How the voltage will, from after finding this IT, you can multiply with the voltage across, you can find out the voltage across the capacitor also, how it is getting increased. Okay, so slowly it will go and it will reach the voltage V. So that is the thing. So now to restrict how much value, say your power supply is 24 volt and it having a peak rating of say 5 ampere. Now you have to restrict that current. So your R will be 24 by 5. This much ohm we have to use for pre-charging. I am talking about pre-charging. So that you can the power rating of the resistor you can reduce, because this is not the continuous rating, because once the capacitor voltage, so you have to find out at t is equal to what time the capacitor voltage is achieving, it's a thumb rule, V by 3. So till the capacitor voltage is achieving V by 3, let us charge through the resistor path so that the inrush current is restricted. And once the capacitor is charged by V by 3, then that inrush current will not flow. There is no short in the circuit. Now you can bypass the resistor. So this is all about how to design how to select the resistance, and your power rating of the resistance accordingly you can set. Power is I square R. So how much power you need, and for what, it's not continuous time, you can find out to reach that V by 3 what should be the time, and during that time only it will flow that 5 ampere. After that it's not continuous rating, so your size of the capacitor resistor also it will reduce. So this is the way to calculate the precharging resistor. Okay, now we will discuss about the PWM. So in PWM, basically we are going to generate it through some timer. Timer is a very important component in microcontroller, which is used for several purposes. So the timer, what is doing, it is counting from one value to its maximum top value, and again it is coming to 0, then again going, it is like that only, it is counting. So there are different timer. One is fast timer. Fast timer is, it is go like this and immediately it is dropped to initial and going. This is called fast counting. Another kind of counting is there, which is called phase correct PWM or phase correct counting. So this, what is doing, it is from one initial to, it will going to maximum, then again coming down. It is like this. So we are going to use, we will be using this phase correct. We will be using this phase correct PWM, okay, which is like this basically. Why so, you will understand. So this, while the initial it is going to maximum, this is called up counting, and this is called down counting. Okay. So this is basically the timer. So now I am going directly to the code so that it will be, you can understand. So already here, this is already, this is a header file, and here I am using one variable I counter. Now pin config. In pin config, you see, in pin configuration, I am using, why these two pin? B1 and B2. Let us see what is this B1 and B2. You see, PB1, this PB1, here you see one thing written, OC1A, that means output compare register channel 1, and this PB2, output compare register 1 is for the timer number, 1 is the timer number, and A is the first channel, B is the second channel. So the output compare register of timer 1, we are using both the channels. Okay. The next thing I have used here, timer initialization one function. So here I am writing. Already you are familiar with that special register SREG, because I am going to use some interrupt. So whenever we are going to use some interrupt, basically we will be using the global interrupt enable, which is the 7th bit or I bit, so that I made high here. TCNT1, that is the data register of timer 1. So always it is better to initialize it to 0. Now I am going to few more registers. TCCR1A, timer counter control register channel A. Let us see that. What is that register? TCCR1A. You see, this is the register 1A. So we will be using all the bits here. Okay. So you see, the 7th and 6th bit is basically the channel A, and 5th and 4th bit it is for channel B. So what I made here in code, for 7th and 6th I made 1 for 5th and 4th I made it 10. Why so? Now if I go to PWM mode, you see this table, this is the, as I told, I am using output compare mode, and it's a phase correct PWM mode. So if it is 1 then set OC1A on compare match when it is up counting and clear while down counting. What is that? Say for this cycle I am setting the compare value here. For this cycle I am setting the compare value here. What will happen if I define that 1 that means set while up counting and clear while down counting. That means once it is counting, it is going up, count, and here it is match. In this position that pin will go high. And it will maintain. And while down counting, if it is matches, it will clear. Similarly here, while up counting, once it is match, this pulse will go high and maintain the same state, and once the compare matches while down counting, it will clear. Okay. Now for a square pulse or for any pulse, duty cycle, say this is your T on and this is your T off, and this is your total period. Basically your duty cycle is nothing but T on by T. This is the duty cycle. So with this, what we will understood, that if I set the different output compare register value, then the duty cycle of the PWM can be changed. Okay. Now I am going to tell you about the second channel, why it is set 10. Why it is set 10. So you see 10 is what? Just ulta. Clear while up counting and set while down counting. Now say for a particular thing, this is for 1-1 setting and this is for 1-0 setting. Now let us see what 1-1 setting, what is going to happen. So in 1-1 setting, it will be set while up counting and clear while down counting. So you will get a pulse like this. Okay. But for 1-0 setting, it's already set, and this position you will get clear, it will maintain, and this position you will get high. Similarly, it is going to happen like this. Okay. Now you recall I told about the dead time in the last lecture. When there should be some gap between the two complementary pulses transitions. Now you see, I am getting that period, this time. Here both the pulses are 0. Both the pulses are 0. So I am able to generate the dead time. And how to calculate the how much the dead time it will be, I will explain you. So now in the code, these 4 bits are very clear. Now I am coming to the other bits. Other bits what? This WGM bit. This is waveform generation bit of that register. So here 2 bits are in register A and other 2 bits will be in register B. You see, this is the register B. So here these are the other 2 bits. So now if you see here, these 2 bits I set 1-1 and other 2 bits in the B register, that means 3rd and 4th bit, here I made 0-0. So this is the 3rd and 4th bit, I made 0-0. So basically in WGM I am setting that 4 bit 1-1-0-0. Now I am going to the WGM setting. So what I am using? Sorry, I am using, this is 1-1-0-0. This setting I am using. 3rd. So phase correct 10 bit PWM. Correct? So 10 bit means the entire period of the PWM from here to here, it is 10 bit. So 2 to the power 10 minus so this is 1024. Okay, it is 1024. So if I give 1024, what will happen? We will get full duty cycle, always high. If I give 512, it is 50% duty cycle. Okay? If it is 256, it is 25% duty cycle. Like that way, it will vary. Okay? Now, what should be the period? This period is what? Because otherwise I can't calculate this dead time. For that, if I go to the code, here these 3 bits, I am using 001. What is that 001? What is that 001? You see, this register B, these 3 bits are pre-scalar bit. So pre-scalar bit 001 means here no pre-scaling, means clock is divided by 1, same as it is. So now if you see the formula for PWM, this is the timer counter. So you have to see the PWM. Let us search here PWM. You see, this is the timer 0 and 1. So we are going to phase correct mode. So for phase correct mode, this is for timer . So we are talking about timer 1. You see, for timer 1, the PWM frequency is clock frequency divided by 2 into prescaler into top. Okay, top means the maximum value. So here it is 16 megahertz. My crystal oscillator frequency is 16 megahertz divided by 2. My prescaler is 1 and my top value is 1024. Okay, so now it is 8 megahertz divided by 1024. So your PWM frequency is 7.8125 kilohertz. Okay, 7.8125 kilohertz. So my entire period, the T, is equal to 7.8125 kilohertz. Sorry, 1 by this much kilo, that means that much millisecond. That is my total period. So you found the period. What is the period? So here F is 7.8125. So my period is 1 by F, that much. So this entire period is covered by how many counts? 1024 counts. So unit time, say it is kilo. It is kilo means you can convert it to microsecond. So that means T is equal to 1, this is microsecond, divided by 7812.5. So it is 128 microsecond. 128 microsecond. Full period. So nanosecond means into 10 to the power 3. That means, sorry, 128 this much nanosecond. Okay, so this much nanosecond is covered by 1024 counts. Okay, so per nanosecond is covered by 1024 divided by that 128 into 10 to the power 3. So suppose my dead time is say 100 nanosecond. So this is 100 nanosecond and this is 100 nanosecond. So total I have to reduce 200 nanosecond. So 200 nanosecond means into 200. So this much count I have to reduce. Then only I will get the dead time in both side 100 nanosecond, 100 nanosecond. So this way you can define your dead time. So while you will be working, you will be doing it. Another register I am using, this is timer interrupt mask register. So if you see that TIMSK, TIMSK1, you see in TIMSK1 I am using this one only. What is that bit? Timer overflow interrupt enable. So once the full counting is over, one interrupt will be generated, and that there only. So this is my as I have used timer overflow interrupt. So in OCR1A register I am giving this duty cycle. Okay, 50% duty cycle. So both the pulse, now the inverted pulse will generate with a duty cycle of 50%. Okay, so let us compile and open this. Sorry, my computer is very slow. I don't know, sometime what happened, it's become dead slow. Now you see here I have connected the two channel A connected with OCR1A, channel B connected with OCR1B. Now let us take that text file. Let us run. See, now the channel A, if I slightly shift it, see the channel A, it was yellow, which is giving non-inverting PWM, and channel B, it is giving exactly inverting PWM. 1, this also I will make 1. Okay, now this channel I will shift slightly down, this also I will slightly down. You see, now you see channel A and B, and the time also, time I will change slightly. Okay, so you understand that exactly now it is exactly the same. But if I want to generate the dead time, what I told you already learned how much count is to be reduced based on, say here I am reducing say some count, so 450. Let us see what will happen. Now if you see, now I am slightly both the pulse I am coinciding. Now you see, you are getting some gap. So this is the basic concept to generate dead time. You see, now in that gap both the pulses are 0. So you can set your own dead time based on the data sheet of your IGBT or MOSFET, whatever may be. So, but here it is a fixed duty cycle. I will next lecture, because we are going to make one sine wave inverter, so that I will explain in the next class how to generate the sine PWM. This is a fixed duty PWM. With that, because sine PWM slightly complicated, so that's why I am not club with this. So here you understand how to generate the dead time. In the next class you will understand how to generate the PWM, both club together, then you can generate the dead time. Okay, so how to check, let it close, otherwise after writing the code, how to check whether your dead time, whatever you are given, everything is correct or not. So this is your power supply. So power supply having one ammeter, in this regulated power supply itself having one indicator. Now here all your capacitor, everything, it will be there, that will be there, and this is your inverter. This is the two line and neutral, and this is your triggering. This you are giving the PWM from microcontroller. Okay, here one switch will be there, you on off for. Now you precharge the capacitor, give the triggering pulse to the microcontroller, on the switch. Now load is open, so this ammeter should not give any current. Ideally it should be 0. That means there is no short happening in your, now your PWM, that means your PWM is correct. Normally it will not get, you will not get 0 because there are some other leakage will be there through the switch also due to a minority carrier flow. It will be some milliamps, in the range of some milliamps. If that is there, then your dead time is correct. So this was all about today's class.